Okay, so in this topic video, we're going to look at a thing called ANCOVA. So what is ANCOVA? Well, basically, it's where you have a regression, a linear regression. But what you've done is you have two types of predictors. You have a predictor that is a quantitative variable and a predictor that is a categorical variable. And you can consider three types of model. One where you just do a single straight line to the whole data. One where you have extra lines, one line for each level of the categorical variable, but they're all parallel. Or the final one, what we call separate regression, where you have a separate line for every single level of the categorical variable. So no longer is the slope parallel. And you can use various ways of deciding which is the best model. So we're going to illustrate this by looking at the CARS dataset, or the MPG dataset. So first of all, let's go to the iPad. So what we've got here is we've got a simple scatter plot here. We've got a simple scatter plot here. If I could ever zoom in, that's better. So we've got a scatter plot here where we have on this axis we've got our CTY, and on the other axis we have the displacement. And first of all, we want to look at this relationship, and we can see that it's a bit curvy. It sort of comes down, but if we try to fit a straight line like this, we could say there's a negative relationship that as displacement goes up, CTY goes down. So the next thing we're going to do is we have an extra variable we could look at in this, and it's called drive. So what I've done here is I've just fitted three separate lines. So we've got this line here in the light blue, which is for front wheel drive. We've got our four-wheel drive, and then we've got our rear-wheel drive. And if we look at the relationship, first of all, we still see that as displacement increases, CTY decreases. We also see that the lines are not all the same. They would have different intercepts. So this would have an intercept up here. This would have an intercept here. This one, if I guess, would have an intercept about here. And also the slopes look different as well. So how could we model this? And do we need to model it? Is there a significant difference between these? Maybe one single line would do. So we will start by considering identical regression. And one of the key things to think about whenever you're doing any linear modeling is, what does the design matrix look like? Because the design matrix, to some extent, tells you how to get information out of a linear model, how to get the interpretation. So let's think about this data here. And let's think about how we could actually do our linear regression. You're going to let me... I'm going to have to go. I will go down to the bottom to do this. So let's think about what our design matrix would look like if we're down here. Oh, that's better. At last. Let's have a little bit of grid. So we've got this data. And so the first one is a four-wheel drive. It has this displacement and this CTY. So we only really care about the first bit of data. And it's 1.8, 1.8, 5.3. So let's think about our design matrix, which we normally denote by X. Well, if we were doing these first ones, we always have an intercept. So we'd have a 1, a 1, and a 1. And if we do an identical regression, we don't care about the drive at this point. All we care about is the displacement. So we would have a column for the displacement here. And if we look at the values, we've got 1.8, 1.8, 5.3. So the first car has a displacement of 1.8, and then the next one has 1.8, and the final one has 5.3. And just over here, I'm going to write down what the actual categorical is so we can use it, and I don't have to keep scrolling. So 4FR. So we've got 4, we've got F, we've got R. Okay, so the next question is, if that's the identical, could we do the parallel? Well, with the parallel, we're going to now add in extra intercept for each of these various drives. And the way we do that is we go over here and we see that we've got we have 3 levels. So we're going to add 2 extra columns. The first one would be so how do we decide the columns? Well, we look at these alphabetically and say which one comes first alphabetically. In this case, the first one alphabetically is 4. So we're going to need a column for the other 2, the F and the R. So we're going to have a column for the F and a column for the R. And the way these works is they're going to be a 1 if you're front wheel drive, a 0 if you're not. With the R, you'll be a 1 if you're rear wheel driver, a 0 if you're not. So the first one is 4-wheel drive, so it's neither a front nor a rear. Next one's a front, so it will be a 1 and a 0, and the final one would be a 0 and a 1. So if you can think about it, this F is the extra bit you will add to the intercept. So the F is the extra bit you add to the intercept to get the new intercept. And the same for the rear, it's the extra bit you add to the intercept to get it. What if we want now what we call our separate regression? Well, now not only do we need to change the intercept, we also need to change the slope. So we're now going to have a thing that is going to be called displacement F and displacement R. And the way we get this column, because it's an intercept, is we multiply this column by this column. So this will be 0, because 0 times 1.8 is 0. This one will be 1.8, because 1 times 1.8 is 1.8. This is 0. This one, we've got 0 times 1.8 is 0. We've got 0 times 1.8 is 0. And we've got finally 1 times 5.3 is 5.3. So this would be your simple one. This would be your identical. If you then did all of this, this would be your parallel. And finally, if you did all of them, this would be your separate. Easy. So that's what R does under the hub. So if we look at the parallel, what it's done is you can see here, it's estimated the intercept, so that's that number, and it's estimated the slope. Okay, so if I wanted the model for that, if I wanted to write it down, so we'll come down here and we'll say, let's do the parallel. No, sorry, not the parallel. Let's do the identical. It's going to be basically CTY equals, we need to get the first number. What's the first number? All the way back up it. It's 25.9915. So it's 25.9915 plus, let's get the slope. Well, it's probably, actually, I should have probably written negative there. Yes, negative 2.6305. So let's change that to a negative 2.6305 displacement. So there we just get one line. That is our relationship. Now let's think about parallel. Well, let's go and have a look at the numbers. So we now have in our numbers, this is the coefficient for the intercept, this is the slope, and then these two are our extra bits that we're going to have either for the front wheel drive or the rear wheel drive. So if you come down here, we're going to end up with 3 models. Let's do the first model, the 4-wheel drive. Well, that is just going to be CTY equals our intercept, which was the 23.9796, minus our 2.3385 displacement. Okay, well, let's look at our front wheel drive. Well, now our CTY is going to be the same intercept to 23.9796, but we have an extra bit, the plus 2.2752. Let's go and check that. If we go here, there's the 2.2752 that we talked about. So there's that number there. but it's minus the same slope. It's parallel. So it's minus 2.3385 displacement, which basically ends up being equal to, I wrote this down before, there we are, 25.9548 minus 2.3385 displacement. So that's our front wheel drive. We've done our four wheel drive. Now let's do our rear wheel drive. So it's CTY equals our intercept 23.9796 plus the 2.5045. Let's quickly do a sanity check to make sure that that matches what we think. Yep, it's that number here, which is good. Minus, well, a little bit deja vu, 2.3385 displacement. And we do that calculation. Jono got, so there's only about a 50% chance it's actually right, because he's not very good at mental arithmetic. But 26.1841 minus 2.3385 displacement. So the key idea here is we take the intercept and we sort of adjust it for each of the extra two levels beyond the four-wheel drive. What about the separate? Well, the separate, we're going to do that sort of concept twice. We're going to adjust the intercept and we're also going to adjust the slope. So the first one is always the easier one, which is the four-wheel drive. We often call this one the one that's sort of doesn't have its own column, the reference level. So in this case, this is CTY is equal to 22.5914 minus 2.0663 displacement. And just to check, if we go up here, we can see that if I go into this figure here, this was the intercept and this is the slope. These two numbers are going to be my adjustments to the intercept, and these two numbers are going to be my adjustments to the slopes. So let's now do that. Let's do the front wheel drive. That's going to be CTY equals 22.5914, and our adjustment to the slope is plus 2.1285. Then we've got plus, now our basic reference level slope is the 2.0663, the negative there, minus the adjustment is the 1.3529 displacement. And if I do those calculations, I ended up with 28.7198 minus 3.4192 displacement. Cool. So here's the extra adjustment we got from that column. Here's the extra adjustment we got from the other column. Rear wheel drive, for completeness, let's do that. So it's going to be CTY equals 22.5914. Our adjustment is minus 3.0124. Plus the basic slope is the 2.0663. The adjustment this time is we're going to increase that slope by 1.0039 displacement, and when we put all that together, it equals 19.579 minus 1.0624 displacement. So there you see, we can now get this idea that we're getting multiple slopes. It's really cool. You know, if you think about it, you've just fitted one linear regression model. In the case of the separate, just one linear regression model. There's a load of extra columns in your design matrix, but now we can get three separate regression lines out of it. And this is really useful. You will find that the data you look at often has continuous quantitative variables and categorical variables, and you can fit these multiple things. And it's not usually just, one continuous and one categorical. You'll have multiple categoricals and multiple interaction terms. And you can have really complicated relationships by including these in with, two-way, three-way, four-way interaction terms. Once you get beyond this basic, it gets very hard to visualize or think about it. But, I will quite often have, 200 predictors. I look at a lot of genetics data, and in genetics, I may have, 100 SNPs, which is a type of mutation. And each of those will have usually 3 levels, and you've got all those, and then you'll have, weights and height and things like that. We might be predicting, something from this, and you get these really complicated interaction models. But it's just this. This is where we start, and then we will have to work out those complicated models. And they might say, well, if we're this level and we're, this height, can you now tell us what the relationship is? So anyway, there's a good starting point. There's an example of what we call ANCOVA, all done, and we'll see you next time. Thank you very much.